Hello and welcome to class number 8. We're going to cover sections 4.3 through 4.5, which deals with present worth analysis, continuing that, and something called capitalized cost, and we'll discuss that. And these lecture notes, as usual, will be posted on Blackboard in Module 4, since this is Chapter 4. And the video that I'm now recording and that you're watching will be also recorded in Module 4. I encourage you to work as many problems at the end of the chapters as you can. And that'll prepare you for the homework assignment, which is a large part of your grade. Now, the section 4.3 deals with present worth analysis of of alternatives which have different life lengths. Now, in fact, you cannot compare alternatives with different life lengths by present worth or any other method. You have to get some kind of a common life length. And the author discusses some methods for doing that. In section 4.3.1, he talks about a fixed study period, where the company decides some number of years is what they're going to look at, and then all the projects have to somehow fit into that fixed study period. Another method is called the least common multiple of lives. And this is kind of an interesting method in the sense that suppose you had two projects, say project 1 had a life length of 3 years and project 2 had a life length of 5 years, and you're trying to compare these two. Which one is better? Well, you can't compare a 3-year project to a 5-year project. So what you do is you say, well, if we repeated that 3-year project 4 times so that we had a total of 5 cycles, they would end at year 15. And then if we repeated the 5-year project 2 times, or total of 3 cycles, it would also end at a common length of time, which would be 15 years. So you'd use a 15-year period and assume the cash flows exactly repeat themselves. Now, certainly you and I both know that's not really realistic with inflation, with changing in prices and so on and so forth, but that's what we have to do to be able to compare two projects that have different lengths on a common time frame. So we get this common time frame by choosing the least common multiple of lives. And if you had 3 and 5, you'd be 15. If you had a 3 and a 6, well, the 3 could be repeated once, and so you had 2 cycles of the 3, and then 1 cycle of the 6, you'd have a common multiple of 6. So that's the way the least common multiple of lives works. Another totally different concept, and I'm not sure why he deals with this, is called a future worth. Certainly we know how to calculate the future value or future worth of a cash flow by now in the course, but he does this and basically uses either of the 2 periods, the study period method or the least common multiple of lives method. And so the future worth is really not a present worth deal, it's a future worth. But if you have a common time frame, if the present worth of A is bigger than the present worth of B, then the future worth of A would be bigger than the future worth of B, because it's just some constant F given P at some rate for the same number of years in both cases gives you a future value. So, you know, it doesn't matter whether you use present worth, annual worth, or future worth. Those three methods will always give you the same ordering of the projects. In other words, if project A is better than B when you look at it from a present worth standpoint, it'll be better than B when you look at it from a future worth standpoint. It'll also be better than B if you look at it from an annual worth, a uniform series standpoint. The next section of the course, of the textbook, deals with something called capitalized cost analysis. The capitalized cost is defined as the present worth of an infinite uniform or A series. So now the present worth of an A series is called the capitalized cost. It could be more generally spoken of as the capitalized value, because if the A series was a positive number, then its capitalized value would be a positive number. And it turns out that if you take the limit of the present worth, the algebraic formula, P given A I N, and I'm not going to write it out here for you, but if you take the limit of that algebraic formula as n goes to infinity, so that's an infinite A series, take the limit, it turns out that that whole thing falls out to be 1 over I. So the limit as n goes to infinity of P given A I N is equal to 1 over I. So the capitalized cost is simply the annual value divided by the interest rate, or the annual worth divided by the interest rate. A and AW, P and PW, F and FW, they're all the same thing, okay? Well, I'm sorry, A and AW is the same thing, P and PW is the same thing, and F and FW, future value, future worth, whatever. Now, if you solve equation 4.2 for A by simply multiplying through by I, you get the capitalized cost times I is equal to the annual equivalent, or the uniform series A. And so rather than spend a lot of time working through all the examples in the book, which I recommend you go there and you read through them, make sure you understand them, I'm going to work some homework problems for you. And we'll start with problem 4.7. Problem 4.7 says, a manager of a canned food processing plant is trying to decide between two different labeling machines. The photocell unit will have a first cost of $26,000, annual operating cost of $4,800. That's annual cost, so that's per year, and a service life of 4 years. So this machine will last 4 years. The capacitive sensor unit will cost $32,000 to buy and install, and have an estimated annual operating cost of $2,100 during its 4-year life. So they both last 4 years. So this is an equal life, two alternatives, and we're trying to choose the best one. Now, there's no revenues given, so the do-nothing alternative is not an option. So we want the one which has the least cost present value. The author says use the interest rate of 9% per year, and which is the best value based on present worth analysis. So I is equal to 9% per year, and he doesn't say compounded what, so we assume compounded annually. So you assume it's compounded in the period for which the rate is given, if in fact it's not specified. Certainly, if you're signing a contract to buy something, I would find out what the compounding is, if you are not told that. So let's look at the photocell unit. That's the first one. It costs $26,000. So you have this 26,000 at time 0, and then the annual operating costs are $4,800 a year. And that's a uniform series. And both of those are actually negative. That's a p-value and that's an a-value. Both of those are negative. And so I wrote the present worth equation at 9% is minus 26,000. That's at the present time. Plus, this should be a minus, plus a minus 4,800. So I'll just make this a minus sign here. Minus 4,800, p given A, 9% for 4 years. So we get the present value of this, and essentially take the present value of this. Both of those are negative, so they're additive in a sense, and we'll get a fairly large negative present value. If we look at the capacitive sensor unit, that's the other alternative. We have this minus 3,200 as a present value. That's the initial cost of that machine. And it runs, this is a minus as well, it runs $2,100 a year annualized cost for 4 years. That's a uniform series, a little bit smaller series than the one for the photocell unit. That's a minus $2,100. And so we have minus, the present value is minus 32,000, minus 2,100, p given a, 9% for 4 periods. And you can crank those numbers out and come up with a solution in both cases, and pick the one which costs the least. The next problem I'll work is problem 4.28 in your ebook or smart book, and this problem states that machines that have the following cost are under consideration for a robotized welding process. Use an interest rate of 10% per year and present worth analysis. Which machine should be selected? And then he has parts A and B, and he wants you to use the factors, wants you to use spreadsheet. I don't care. I mean, I usually use the app, so I'm not concerned with how you get the answer. I just want to know that you can read the question, set it up right, and then work it by some method, okay? Whether you use Excel or factor method, as I said, I always use the app. And then the second part of the question says, okay, and notice that these two machines have unequal lives. Machine X lasts 3 years. Machine Y lasts 6 years. So in order to do this, it turns out the least common multiple of lives is fairly convenient. It's 6 years. So that's 1 cycle of machine Y, but 2 cycles of machine X. So we better draw the cash flow diagram so we can get to this. So the solution for parts A and B is that I is equal 10% per year. Again, compounded annually. The number of years is 3 for X, but the number of years is 6 for Y, so the least common multiple is 6. So that's what I'm going to draw up as my cash flow diagram. Now, the first cost for X the cost to buy the machine and install it is $250,000. So we'll put that here. And sometimes, you know, when I'm working a problem and everything is negative, which is not in this case, I'll just let cost be a positive. But in this case, I can't because I have a positive salvage value. And again, the do nothing alternative is not an option here because there's not any revenue given except for the salvage value. So we don't consider do nothing when there's no operating revenue available. So the operating and maintenance cost for each year of machine X's life of 3 years is $60,000. So I'll put the $60,000 for each of the 3 years. At the end of the third year, you get a $70,000 salvage value. These are $60,000. But what happens at the end of the third year? This machine its life is over. We have to buy a new machine for the second cycle. And that happens at the beginning of year 4, which is the same thing as the end of year 3. So we'll add to this $250,000 again. I put P equals, but it's really not at the present time. It's just the initial cost of this machine. And this machine is going to have a $60,000 annual cost again. And then at the end, so this $60,000 now goes for all 6 years. And then we'll get a salvage value here of $70,000. So that's the cash flow for this machine. But what we really need to do is net out this year 3 cash flow that involves both the salvage value and the new cost. I'm going to leave the $60,000 because it's part of this uniform series of 6 cash flows. So I'm going to leave the $60,000. I'm only going to net out these 2 items. And that's a plus 70 and a minus 250 will end up being a minus 180. And then this number here is out here as well. So the present worth of X is this minus 250. Take care of that, okay? Check that one off. Minus 60, P given A, 10% for 6 periods. Take all of those, check those off. You got them taken care of. Now you've got this and this left, okay? So I'm going to take the plus 70 and the minus 250. That's a single payment here at time 3. I'm going to go P given F, 10% for 3 periods. That will bring those 2 things back to time 0. And then I have the plus 70 out there, and it's out there 6 years. I'll bring it back to the present. So that is the cash flow and the equation to get the present value of that cash flow for machine X. Machine Y is only 1 cycle, so it's a little bit easier. The first cost is minus 430,000. So I'll put my minus 430, 430,000 here at time 0. And then it costs $40,000 a year to operate it. So you have a $40,000 series of 6 years. And that's a minus. And then you have a salvage value out here of $95,000, which will need to be accounted for. That's a P given F. So for machine Y, you have a present value of minus 430. That's at the present time. Then you have a uniform series, 40,000. That's a minus sign. Minus 40,000, P given A, 10% for 6 periods. and then you have the plus 95, and that is a plus sign because that's a salvage value. P given F, 10% for 6 years. Plug in, and I'll let you work out the numbers if you choose to work this problem. It may be a homework problem, it's possible. The C part of this problem asks you to use a fixed study period of 3 years. So everything has to end at 3 years. He further states in the problem statement that, well, let me bring it back up here and show you where he says, assume the market value of Y remains 95,000. Remember, that was its salvage value. He's going to say, he's telling you to assume, even if you get rid of it at 3 years, still only worth $95,000. So let's look at A, and I'm going to put my cash flow for A, which is here. I'm going to put this on the page so I can see it. And I've got an initial cost for machine X of $250. That's the same thing we had before. And then you had minus $40,000 a year for the 3 years. 60,000, I'm sorry. 60, 60, 60. And you had a salvage value of 70 at the end of the life, which is 3 years. So that's the cash flow. And we're going to find the present worth of that now. So the present worth is minus 250. That takes care of that one. Minus 60. P given A, 10% for 3 years. And then you have a plus 70. P given F, 10% for 3 years, and that will give you the present value of machine X. Now machine Y really would have lasted 6 years, but he's saying cut it off at 3. We're going to use a 3-year study period, and that one cost $430,000, recall. So we'll put the 430 here. It has annual operating cost of $40,000 a year, a little bit less than machine X. Again, remember that actually, this is a minus 60 here. That actually went for 6 years, but he's cutting it off at 3. And then he's saying a lot of times when you cut it off and the machine has a significant life length remaining, the salvage value will be more than what he estimated at 6 years. But in this case, he says estimate 95,000 no matter what. So we're going to put the 95,000 here, and we'll find the present worth of that cash flow. Well, you got the minus 430, again minus, and then you have the minus 40 again. And then you have the plus 95, P given F, 10% for 3 periods. This is 3-period A series, plug and chug, and you should be able to get an answer for that. So we'll work one more problem. Problem 438 is a life cycle cost problem. And I know these numbers may be difficult for you to see, but I'm going to specify them, and then I will post these notes so you could have the notes when you view the video lecture. So it says, the Health Department of Winter Park plans to develop an upgraded software system to assist medical personnel in treatment of opioid-addicted patients. The program cost estimates approach discussed earlier, well, I don't know, has been used to make estimates for a 10-year program. with categories of development, programming, operating, support cost, there are 3 alternatives under consideration, identified as A, a tailored system, B, an adapted system, and C, the current system. The cost estimates are summarized below. Perform a life cycle cost analysis to identify the best alternative at 8% per year. And then he says using different methods. I'm not concerned with how you get to it method-wise. I'm going to use the app. Let's start back with System A and let's look at it real carefully. This says you have $250,000 now, and you for development, and you also have, and I'm going to draw a line here to separate System A and B, and another line separating C and D. I mean B and C. And so you have $295,000 now for development, $45,000 now for programming. So that's $295,000 now. And all the other costs are in years 1 through something, 1 through 4, 1 through 4, 1 through 10, 1 through 5. So we'll have to be very careful that we basically add the right numbers for what years, for System A especially. System C will be very easy. It's a straightforward uniform series. Anyway, for System A, right now we got minus $295,000. In years 1 through 1, we have 150 and 35. Those two are both in years 1, and so are these two. So you have 150 and 35 is 185, and 50 is 235, and 30 is 265. So that, and those are for both years 1 and 2, because this one doesn't end till year 2. So we have 265, 265. Then in year 3, this one goes away. So we go down by 35,000. We still have this, this, and this. This is 150, 50 is 2, 230. So we have 230 until this one goes away at the end of year 4. And when this one goes away, we're going to drop by 150,000. So we'll just have 50 plus 30, which is 80. And then at the end of year 5, the 30 drops out. So we now have just 50 from then on. So this is A. For B, we have 10,000 now cost, and we also have 45,000 during year 0, which is essentially we put it at the end of year 0, which is now. So that's a $55,000 now. So that's minus 55 here. And then in years 1 through 3, we got 30. Years 1 through 10, we got 80 and 120. So we've got 150,000 in years 1 through 3. And then at the end of year 3, this 30 drops out. And these other two, the 80 and the 120, I'm sorry, the 80 and the 40, which add to 120, continue on the rest of the time frame. And then finally, System C is just 175 all the way, all 10 years. So we need to find the present worth of all of this stuff for the 10-year period at 8% per year compounded annually. So basically, I wrote the equations for that, and because I'm going to show you the cash flow for A, you got 295,000 now, so that's there. And then you have 265 for 2 years. So that's like a uniform series for 2 years. When you find the present worth of that series, it's at time 0. Okay, it's at the beginning of the first year of the series, which is the end of year 0. So that's 265 P given A, 8% for 2 years. That takes care of those two. and we already took care of that one. Now we have another 230 for 2 years. Well, that's a little A series, but where will it be when I do P given A? It'll be at time 2, the beginning of year 3, which is the end of year 2. So that will be P given A for 2 years, and then P given F to get it back to time 0. So 230 times P given A, that should be a 2. And that is a 2, P given F for 2. Then we have an 80,000. It's there by itself. It's not part of a series. It's at time 5. So I go P given F 8% for 5 years. That gets the present value of that one. And then finally, you have a $50,000 series that runs the remaining 5 years. So that's going to be 50,000 P given A 8% for 5 years, then P given F 8% for 5 years, because when I get the present worth of this series, it's going to be here, and then I want to take it back to 0. So that does that. And then the cash flow B, we have minus 55,000 at time 0. Then you have 150 for 3 years. That's 150 P given A 8% for 3 years. That takes care of that. And then you have 120 from then on. So it's 120 P given A 8% for 7 years. And then P given F 8% for 3 years. Because once we get the P given A, it's here. We need to bring it back to time 0. And then the 175 P given A 8% for 10 years. And that should give you the answer to 4.38.